On November 18, 2026, at 16 minutes past 2 in the morning Pacific time, a piece of 1970s machinery will cross a line that nothing built by human hands has ever crossed. Voyager 1 will be 16,094,799,096 miles from Earth. At that moment, a radio command leaving this planet will need a full 24 hours to reach it. One light day. It has taken 49 years of continuous flight to get there. 49 years of falling outward through the dark, past Jupiter, past Saturn, out through the edge of the sun's bubble, and into the space between stars. 49 years, and a signal covers that same distance in a single rotation of the Earth. Now hold that number in your hand, because we're about to do something to it. Multiply it by 365. That is 1 light year. Not a light day, which took us half a century to reach. A light year, and the nearest star system to our own, is 4.5 of them away. This video is not about how far that is. Distance is easy. This is about what actually happens inside that gap. What it does to metal, to time, to the idea of going somewhere and arriving. Because the first light year is not a distance we have not crossed yet. It's a wall, and every direction you push against it pushes back in a different way. The fastest object human beings have ever built is not Voyager. It's a spacecraft roughly the size of a compact car, and on Christmas Eve of 2024, it passed within 3.8 million miles of the surface of the Sun, moving at 430,000 miles per hour. The Parker Solar Probe, fast enough to cross from Philadelphia to Washington in about a second. Here is that same number expressed differently, 0.064% of the speed of light. 64 thousandths of 1%. That's the ceiling. That is the fastest we have ever made anything move, and it only reached that speed by falling into the gravity well of a star, which means it cannot keep it, and it's not going anywhere. It is in orbit. It's a stone whipped around on a string. Voyager 1, which is actually leaving, travels at about 11 miles per second, 38,000 miles per hour. At that speed, 1 light year takes roughly 17,600 years. Take a moment with that figure. 17,600 years ago, the last ice age was at its maximum. There was no agriculture, no writing, no wheel. Every human being alive was a hunter. If a probe had launched at that moment at Voyager speed, traveling every second of every day since, it would be arriving now at the first light year, and it would still have 3.5 more to go before it reached the nearest star. Even Parker's impossible speed, if we could somehow sustain it in a straight line, would need about 1,560 years for a single light year, longer than the gap between the fall of Rome and this sentence. We're not slow because our engineering is bad. We are slow because chemical rockets convert a very small fraction of a very small amount of stored energy into motion, and there is no version of that arrangement that gets meaningfully closer to light. The gap is not a gap in skill. It's a gap in physics, and it is the reason the rest of this video is not a story about travel. It's a story about inertia. One quick thing before we go further out. If this is the kind of thing you want more of, subscribe and turn on the bell so the next one finds you. Suppose we solve it. Suppose some combination of nuclear pulse, fusion, or laser sail gets a vehicle to 20% of light speed, which is the target of the most serious interstellar concept currently funded. At that speed, the nearest star is about 20 years away instead of 80,000. Problem solved. Except that the space between stars is not empty. It is thin, which is not the same thing. There's roughly 1 atom of hydrogen per cubic centimeter out there, and scattered through it, grains of dust. Individually, they're nothing. A speck of carbon or silicate weighing a fraction of a trillionth of a gram. At walking pace, you'd never know they existed. At 20% the speed of light, they're not specks. They arrive with the kinetic energy of bullets, and they arrive constantly. The physics has been worked out in detail. A spacecraft moving at that speed has its forward surface eroded by dust bombardment to a depth of around 0.5 millimeter over the course of the journey. Hydrogen and helium nuclei streaming in at relativistic energy bury themselves below the surface of the metal and accumulate there, forming bubbles that blister and then tear the surface away in flakes. The same process that damages the inner walls of fusion reactors, except here it's running continuously for 20 years with no maintenance and nobody aboard to repair it. So the leading edge cannot be a hull. It has to be a shield that is designed to be destroyed. Some proposals suggest a block of ice, cheap, replaceable in principle, and it ablates in a predictable way. The vessel does not travel through the interstellar medium so much as it is sandblasted by it, slowly for decades, losing a measured amount of itself every year of flight. This is the part that never appears in the artwork. In the paintings, the ship is clean. In reality, the object that arrives is not the object that left. It's thinner, pitted, a hull that has been under fine, continuous erosion since the day the engines cut, arriving at a star with whatever was left after the crossing took its share. Now, the cruelest problem, and it's not an engineering problem at all. In 2006, a researcher named Andrew Kennedy published a paper asking a question nobody had formalized. If our ability to travel keeps improving and a ship launched today will take centuries to arrive, then a ship launched 100 years from now will be faster. Fast enough, possibly, to overtake the first one in transit. Picture it properly. A crew departs. Generations are born and die aboard. Somewhere in the middle of the crossing, a vessel built by their descendants passes them. It doesn't stop. It can't stop. It arrives decades ahead of them, and by the time the original ship reaches the destination, its people have been made obsolete by their own grandchildren, arriving to find the place already settled by strangers who left long after they did. Kennedy called it the incentive trap. It has a nasty recursive quality. If you know you will be overtaken, you don't launch, so you wait. But everyone who comes after you reasons identically, so they wait too. And the improvement in speed that justified waiting never happens because nobody's building anything. Here's the part usually left out, and it matters because it's the only thing in this video that resembles good news. Kennedy did not conclude that departure is futile. He showed the opposite. Run the equations with a realistic rate of growth and there is a minimum. A moment when the sum of waiting plus traveling is smaller than at any other moment, before or after. For Barnard's star, about 6 light-years out, assuming a growth rate of 1.4% a year, that minimum sat roughly 712 years from the time he wrote. Which is a strange kind of comfort. There is a right time to leave. It's simply not now, and it's not within the lifetime of anyone who will ever read this. And the decision belongs to people separated from us by more time than separates us from the Norman conquest. Everyone expects relativity to be the villain here. The traveler returns young. Everyone they knew is dust, the classic story. It's not the villain, and the reason is worse. Time dilation only becomes significant at speeds we can't reach. At 20% of light, which is already the outer edge of serious proposals, the crew ages about 2% slower than everyone at home. Over a 20-year crossing, that's a matter of months. It's a rounding error, not an exile. At the speeds we actually possess, the effect is unmeasurable. Voyager has been flying for 49 years, and relativity has cost it a fraction of a second. So, the separation from human history is not caused by physics bending time. It's caused by something far more ordinary. The journey simply takes longer than civilizations last. Nobody needs Einstein to be cut off from home. They only need duration. Consider what that means for communication. A crew 1 light-year out sends a message. It arrives in a year. A reply, if anyone is still listening, arrives a year after that. 2 years for a single exchange, and the gap grows every day of the voyage. There is no conversation. There is only broadcast into a delay, and the reasonable expectation that the institution which launched you no longer exists in any form that would recognize your call sign. NASA expects to lose contact with Voyager 1 around 2036, not because it will be destroyed, but because its signal will simply become too faint to separate from the noise. It will keep flying, it will keep pointing at us, and it will pass within 1.7 light-years of a dim red star in the year 40,272. long after the language these words are written in has become unreadable. That is the actual divorce from time, not a paradox, just an object still functioning after everyone who understood it is gone. Halfway, 6 months of light in every direction, and the same again ahead. The popular image of this place is darkness, and it's wrong. The sky out there is not empty. It's full of stars, roughly the same stars you can see from your garden in roughly the same arrangement, because a light year is not far enough to move them. That is the detail that gets under the skin. You could travel for 1,000 years and the constellations would not visibly change. You'd be moving at a speed you cannot comprehend for longer than recorded history, and the view from the window would be identical on the last day and the first. What does change is the sun. It shrinks until it has no disk, until it simply is the brightest star in a sky of them, and then not even that. There is no boundary, no threshold, no moment of departure, just a slow demotion of the thing that made you. And there is no temperature. The interstellar medium sits a few degrees above absolute zero, and there is no source of heat except the reactor you brought and the star you're aiming at, which is too far to warm anything. Every calorie of heat that keeps a human being alive out there has to be manufactured and then defended continuously for the whole crossing by machinery that cannot be replaced. This is the part of the journey with no events in it. No arrival, no departure, no landmark, nothing to measure progress against. Thousands of years of nothing happening in a place where nothing has happened for a very long time and nothing is scheduled to happen again. So what actually happens when you travel 1 light year? The metal erodes, the clocks stay honest, the messages take years and then stop being answered. The people who left are overtaken or forgotten, or both. And the sky does not change, and the sun becomes a star. And the first thing that arrives is not the thing that departed, and there is nobody left who remembers the difference. We tend to describe the light year as a unit of measurement. It's not functionally. It's a quarantine, a distance chosen by nothing and enforced by physics, wide enough that the strategies which built every human civilization, going and looking and coming back, stop working entirely. We're not explorers who have not got round to it yet. We are a species on an island, and the first stretch of the ocean is already beyond our ships. Voyager 1 will cross 1 light day in November. It is the farthest thing we've ever thrown, and it has been flying since before most of the people watching this were born, and it has covered 1/365th of the smallest interstellar distance there is. It's still going. It will keep going after the transmitter dies, after the agency that built it is a footnote, after the language on the golden record is a puzzle for whoever finds it. That is the honest version of interstellar travel. Not arrival, just inertia, carrying a dead machine outward through a silence that has no far side. If 1 light year is this hard to hold in your head, wait until you see what happens at 13 billion. Watch astronomers found galaxies so far away they can't be real. It's on screen right now.